Log on, tune in, find out. Another good idea from Cambridge.
Slava, and thank every of you who came the difficult way from one building to another. So artificial black holes, I will explain what it is. So we start with Lorentz metric. Lorentz metric, so it is have signature plus 1 minus minus minus, and we assume that the metric does not, the variables are x, x1, xn in Rn, and x0 is a time variable. And we assume that metric does not depend on time, so it's called stationary metric. And consider wave equation corresponding to this metric. Corresponding to this metric. Maybe I will not use it. Corresponding to this metric. So this is it's written in such form similar to Laplace-Beltrami, but this is not Laplace, this is wave equation. And G is determinant of the metric, and upper Gij upper indices is inverse metric. Inverse metrics. So now examples of such equations. Examples of such equations. There are 3 examples. One is general relativity, when metric is a solution of Einstein equation in vacuum. And we consider 4-dimensional space R3 times R as pseudo-Riemannian manifold with this given metric. And it's called, this manifold is called space-time, and wave equation describe linear gravitational waves on background of this metric. This is terminology of general relativity. And one of the famous example of such metric is Schwarzschild metric. It's written here. It's written here, the capital R is square root of x squared plus y squared plus z squared. And it is known that this metric satisfies the Einstein equations. Now, 2 other examples are the following. One is propagation of light in moving dielectric. So here, metric is written here. Eta Jk is Minkowski metric, and n of x is refraction index, square root of epsilon mu, and v0, v1, v2, v3 are component of 4 vector. It's written what is v0, what is vj from 0 to 3, and we have w. W is 3-dimensional vector of velocity of the flow. And this is how in relativity you build 4 vector from 3 vector. And c is speed of light in vacuum. All these equation 2 which I wrote, the specific of them that they have different from ordinary wave equations, that they have mixed terms, derivative in time and derivative in x. And physically it's related to moving medium. So this is one example. And second example is acoustic wave in moving medium. Here, rho is density, v, v1, v2, v3 is velocity, c is sound speed. It's not light speed, it's depend on medium, sound speed in the medium. And so this is also written a metric. Now, the title is artificial black holes. So this wave equation will have black holes. black holes corresponding to matrix that is solution of Einstein equation are called real black hole, black or white hole. And black or white hole, which is also in some sense real, but corresponding not to say to this example 2 and 3 or any other example, you called artificial black holes. So this is the title artificial. But then really they exist, but they're not related to general relativity. Okay, so now I formulate, this was many times formulated here, what is inverse problem. So suppose we have smooth bounded domain Rn, you have this equation, and you have zero initial condition, equation in cylinder, yes? Zero initial condition, and Dirichlet boundary condition where F has compact support. And we introduce Dirichlet-Neumann operator. It looks complicated because of normalization, lambda JF. And suppose we take arbitrary open subset of boundary, and we say that we consider boundary value problem of determining metric by boundary measurements on gamma cross 0t. Simply, this means that knowing Dirichlet-Neumann operator F, lambda GF, for all F with support on gamma cross T. So now it is known that this problem is not unique. And if you make changes of variables, y equal phi of x is diffeomorphism of omega on some another domain, and a of x is smooth function, then the changes of variable 6, they transform stationary metric to another stationary metric. This is a general form of transformation stationary metric to another stationary metric. And if metric G and G prime related that these quadratic forms are equal, when y and x are related by change of variable 6, then such metrics are called isometric. So now, if you take change of variable 6, and if you assume additionally that phi of x equal x on gamma and a of x equals 0 on gamma, then, as is well known, the Dirichlet-Neumann operator does not change, so determination is only up to changes of variable 6 and 7. And the theorem here, the main theorem here is the following. Suppose you have two metrics. Suppose that G0, 0, this is upper indices, and G positive and G0, 0 negative. The same for metric G prime. And also, suppose that these two domains have intersection on some boundary, have intersection on some gamma, and the Dirichlet-Neumann operator are equal on this gamma. And suppose this is T should be larger than T0, T0 defined geometrically should be sufficiently large, then the metrics are isometric. Moreover, the change of variable is such that phi equal to 1 and a equal to 0. So this is theorem of solution of uniqueness of inverse boundary value problem. Now, there is another, this is in last moment, I add here another inverse boundary value problem. I first consider this for Schrödinger equation. So we are talking about inverse problem when space in the whole space minus some maybe obstacle. So consider wave equation in domain time times Rn with removed some obstacle. Suppose we have two metrics So we have two metrics, and suppose this matrix coincide outside of a ball, and also they asymptotically Minkowski. So JJK is eta JK plus H JK, where H JK, the eta is Minkowski matrix, and H JK is decaying, short range decay, 1 over x plus epsilon. Then the theorem is, suppose we have these two wave equations. Suppose T is large enough. So consider two initial boundary value problems. No, I'm sorry. Consider two initial value problems. There is no boundary yet here. So initial value problems. So for t equals 0, Cauchy data are the same. For these two equations, Cauchy data are the same. Now, and also the Cauchy data are such that they are 0 inside the ball. Inside the ball, you have 0 initial condition. Outside the ball, you have arbitrary initial condition in L2, H1, etc. And suppose for t, little t equal capital T, you have, no, I'm sorry. It is boundary condition because if there are obstacles, yes? If there is no obstacle, there is no. But if there are obstacles, there are boundary conditions. This is line. I will. This line, yes? This is boundary condition when there are obstacles. And so this is why it's written rightly, initial boundary value problem. But if there is no obstacle, it's simply initial value problem. So suppose that conditions is G0, 0, G0 prime, condition of previous theorem are satisfied. Then and this is the main condition. Suppose that for t equal capital T, the initial condition for u in u prime also equal. Then the conclusion that these metrics are isometric. The metrics are isometric. So it was on 2 pages. I quickly repeat what is the theorem. Suppose you have two metrics, two equations with equal initial condition, arbitrary, but in the ball equal to 0. Suppose for t equal capital T, this condition also coincide. Then the metrics are isometric. So this is such, I think, new type of inverse problem. And proof is very short, reduction to the previous theorem. So this initial boundary value problem exists in L2 and H1, and take difference. Take V is a difference. Then the difference is satisfy wave equation outside of ball, because maybe I did not told this repeatedly, that we assume that two metrics are coincide with the outside of ball. So u and u prime satisfy the same equation. So difference satisfies the wave equation outside of ball, and moreover, by condition, it has Cauchy data, 0 Cauchy data for t equals 0 and t equal capital T. Then if you take Fourier, extend this V by 0 for, yeah?
For t equal to t capital.
To capital.
Only as outside the ball.
Only outside the ball, yes. And so extend this V 0 for t larger than capital T and for t less than 0, and make Fourier transform in time. Then you will have equation, then you have this equation, and this already elliptic equation, and V tilde belong to L2, and this is a relic type theorem that if you have coefficient decaying and solution in L2 outside of ball, then it is 0. I make a reference on Harmander, but I realized that, first of all, I knew that Hiroshi had such results some time ago, and now in recent paper of Isazaki Kurelov is proven for more general equation. So, but anyway, this theorem holds. So, and what this theorem gives, that F tilde, V tilde, that V tilde equal to 0, so U equal to 0, V equal to 0, and this gives that U and U prime are coincide outside of ball cross 0t, cross 0t. So because they coincide, this means that U equal to U prime outside of ball. So they have equal Cauchy data on the boundary of the ball, equal Cauchy data boundary of the ball. So, and combining this with some density theorem, you have that Dirichlet-Neumann operators on the boundary of the ball are equal. Then the previous theorem says that matrix will be isometric. So this theorem, the formulation is new, but the proof more or less reduced to the proof of the previous theorem. This probably written what I said now. Operator, Dirichlet-Neumann operator are equal, so the theorem 1 implies, previous theorem 1 implies that G equal to G prime. Okay. Okay, so now I'm moving to closer to title of the talk, black and white holes. So the feature of such equation, this is because of this mixed derivatives in time in x, that you can have black or white holes. So what is the definition? Domain, such cylindrical domain. This we're talking about stationary matrix. Cylindrical domain is called a black hole. Is no signal or disturbance from inside can reach exterior of omega cross r. And domain is called white hole if no signal from outside can reach inside. I will show a picture later. So now it is easy to show, this is not a theorem, it's some proposition, that in order to have a black or white hole, the boundary should be characteristic. The boundary should be characteristic, where S0 is the boundary of black or white hole. Now it is also quite easy to prove that when you have such inequality, it will be black hole, and when you have such inequality, you have white hole. Always there is strict inequality, either positive or negative. This follows from strict hyperbolicity. So this is definition what is black hole, what is white hole, and boundary of black or white hole is called event horizon. And in this famous example of Schwarzschild metric, R equals to M cross R is the boundary of a black hole. It's the boundary of black hole. So this is a simple picture. So when you have black hole, if you take points on the boundary, the forward cone, half cone of light rays will point inside. So you cannot go outside. You stay inside. And white hole is opposite. If you take on the boundary, the cone point outside. So this is white hole or white hole or black hole. So now one more definition. Ergosphere. Ergosphere is a surface G00 equal to 0. It's called ergosphere. Now, in equivalent form is the following. If you consider spatial parts of equation, disregard everything in time. So, ergosphere is where the ellipticity of the system breaks. Determinant of, if you take determinant of n by n matrix, principal part, spatial part, when determinant equal to 0, this is ergosphere. This is ergosphere. In the case of Schwarzschild metric, ergosphere is R equal to M. And so for Schwarzschild metric, ergosphere coincide with the event horizon. In general, ergosphere is always event horizon is inside of ergosphere or coincide with ergosphere. Coincide with ergosphere. For example, for this Gordon equation, I failed to mention that the case of propagation of light, this equation was first considered by Gordon in 1923, the same Gordon as Klein-Gordon, and the equation of ergosphere is this. This is equation of ergosphere, and in the case when the velocity is normal to ergosphere, then it will be event horizon. Then it will be event horizon. Yeah. So now this is still about inverse problems, but soon I will go straight to existence and stability of black holes. So if you have a black hole, or a white hole, then inside you can change coefficient or metric as you want. This will not reflect boundary measurement. So this is a good example of non-uniqueness of inverse problem. But equation remains, you cannot control anything inside, but can you find the boundary of black or white hole? Can you find event horizon? So this is still open question. The following theorem hold can be proven that you can find boundary, you can find ergosphere. So boundary measurement can determine ergosphere up to changes of variables, up to changes of variables. And sketch of the proof. Sketch of the proof. This is sketch of the proof. The proof, in fact, the same proof for theorem 1, my initial theorem, and the theorem about ergosphere. This is the same proof. So it's proof based on extension of BC method, and this quite short history. BC method was invented by Bereshev and developed by Bereshev and Kurylev and Lassas and others. And I have some new variant of BC method. And so my proof is going this way. How to find ergosphere? You recover matrix. When you recover matrix, then you can find what is G00 equal to 0. So you start from the, you know, from boundary measurement, you know matrix on gamma cross 0t. You start from neighborhood, and you can gradually recover matrix. And when you move inside the domain, the observation time to reach this point inside grows. And if there is no ergosphere, then after final time, you can recover metric in the whole domain. And this will give you theorem 1. But if there is ergosphere, then there's some degeneration approaching ergosphere, and time tends to infinity. Time tends to infinity. I should mention this theorem that an important part of formulation that you need gamma cross 0 plus infinity. You need infinite time to reach ergosphere. Infinite time, you will not recover, never recover ergosphere. You need infinite time. But this method does not require a priori knowledge. If there is black holes or something, you continue, and if no obstacles, you will find. Usual obstacle is also not a problem. If not there is no ergosphere or black hole, you will find all domain. If there are, you will be stuck for infinite time. You will be stuck for infinite time. Okay, so now this is the section about existence of black holes. So consider case of two space dimensions. So we have time and x1, x2, two space dimension. In this case, the equation of ergosphere can be written delta equal to 0. This is determinant equal to 0. So we assume that ergosphere is smooth curve. This is two-dimension. And suppose you have another curve inside S, inside S. We assume that delta, this determinant, is negative because between S and S prime. And there is a condition on, so S is ergosphere, I said this. But on S prime, you have the following condition. So denote by K plus Y the half cone of all forward time-like direction. This means the following. If this is a direction, this is a direction, dot does not mean anything except notation. This is 3 vector in R3, such that this quadratic form is positive for x dot positive. This is cone. And suppose n of y is normal to S1. So the assumption is that this inner product is a positive or negative for all y and all directions. Geometrically, this means that this cone pointing either outside of domain or inside of domain. There are some equivalent formulations too. And the theorem, existence theorem is this. Suppose ergosphere or ergo curve is not characteristic. Not characteristic means this. Not characteristic means this. And suppose this is on S. And suppose that on S1 you have this condition 11. I will have a picture soon on some page in a minute. So then there is then there exists a smooth Jordan curve as 0, which is characteristic. And if it's characteristic, then it is event horizon. So once again, we have such anomalous domain. On larger end, we have ergosphere, which is not characteristic. In the inside, you have such condition 11, which you will see on the picture what it is. And what is the sketch of the proof? So inside our domain, determinant is negative. So you have hyperbolicity. You have in two variables. So you have this family of two characteristics. You can construct two vector fields, which are not equal, not vanishing, not equal except on S, and such this satisfies this characteristic equation. They are global. They are already global. Now consider two differential equations. System of two differential equations for plus and for minus, starting on S. S is ergosphere. Starting on S. Now, there is another ingredient here. We have a null characteristic for hyperbolic equation in 3 dimensions, x0, x1. And this is equation of null characteristic. And the fact is that the projection of this null characteristic on x1, x2 plane coincide with the equations that I wrote before. Projection wrote before. Now, moreover, this is an important fact that you can parameterize, because the time variable over S is not 0, you can parameterize these curves in the plane by time variable as a natural parameter. And then the following fact holds, that we have 2 families of curves, and for one family, when time increases, the curve goes inside domain, and for another family, it ends on domain. There will be a picture. There will be a picture. Without picture is difficult. Yeah. Oh, this is the picture. So you have you have 2 families of curves starting on the S. S is this bigger curve, and one family goes inside, another family ends. In fact, one can show that you have no characteristic are smooth. Yes, so this point is a caustic of this no characteristic. Yes, no characteristic changes projection has a caustic. So now on the smaller, this is S, this is S1. On S1, we have condition that either all curves go inside or all curves go outside. So for example, in the case A, you can see that they goes outside, that this curve cannot reach the smaller domain, because if it reach smaller domain, it should go in this direction, and it goes in another direction. The conclusion is that for this system, limiting set when time increases will be inside. Limiting set will be inside, and there is a, because it's 2-dimensional case, this is important. There is a Poincaré-Bendixson theorem that in this case you have a closed smooth curve, and this will be the event horizon. In the second case, when here you have going outside, this upper family cannot reach the boundary. If it reaches the boundary, it will go inside. So in both cases, you have limiting set, limiting cycle, and this limiting cycle satisfies the equation, and this will be characteristic. This will be event horizon. So this is the proof that the existence of black or white hole existence. And remark, which I will use later, that the condition of this theorem are stable under perturbation of metric. If it was non-characteristic, closed will also not characteristic. If you have this strict inequality, it will be also strict inequality. So this black or white hole, they're stable under perturbation. If you perturb, they still persist. So now, this is a simple generalization for, this is an example. This is a good example. So consider acoustic equation, assuming that parameters are constant, and vector field is A over R, R hat, B over R, theta hat. R hat is radial direction, theta hat is tangential direction, and A, B constant. And we assume that our domain is between circle of radius square root of A squared plus B squared and circle R1, which is less than R. So then ergosphere is this big circle, square root A squared plus B squared. Now when B is not 0, then it will be not characteristic. Now differential equation, this system of differential equation, here natural to write in polar coordinate, it will be, this is one family, this is another family, another family. And for first family, you see that dr over ds A squared minus R squared. So R equal to A is a limiting cycle, limiting a cycle. It will give you black hole. In this case, it will be white hole. If you change A, sign of A, it will be black hole. And so this is the picture. This is the picture. So you see one family. So there is this upper circle, square root is a ergosphere, and this is smaller circle R1 when condition, which I call 11, satisfied. One family going straight from one to another, and the second family is spirals around this bold circle of radius R. RA is a white hole in this case. White hole in this case. You can make many other examples with many, in my papers, many, you can simultaneously have many white and black holes. Okay, I already told you. So now a straightforward generalization for axisymmetric metrics. So axisymmetric metrics, if you use cylindrical coordinate r, phi, and zeta, and assume that metric doesn't depend on the time. We always consider not depending on time, but and also doesn't depend on phi. Doesn't depend on phi. So in this case, you can consider practically two-dimensional case if you disregard phi. Two-dimensional case if you disregard phi. And so you are in two-dimensional case. Now, if you obtain some event horizon, say S, so it does not depend on phi and R. So the event horizon in four-dimensional space will be S equal to 0 cross S1. S1 is unit circle where phi is changing, and R. So if R is time, so for without time, you have a toroid. You have toroid, yes? So it is called rotating black hole, because it doesn't depend on phi, so it will be toroid. Or it can be really rotating, or if it's already around the axis, so it will be rotating but staying on the place, but always is rotating, always rotating. So you can, because it's in two dimension, if you assume that two-dimensional conditions are satisfied, then you will have this rotating sphere. I want to. Be. I have something else. This is, I was saying, simply can be extended easily. So now another topic, stability of black holes or white holes. Stability, I consider stability with respect to perturbation of matrix. So example which we will deal mainly as a great metric, Kerr metric, which is also solution of Einstein equation. This is the this expression of this metric. A little bit complicated, yes. And the ergosphere is this. In a couple of pages, I will have a picture. This is ergosphere. Now, what happens here is that you have two ergospheres, outer ergosphere, inner ergosphere. So now consider restricted ergosphere. What is restricted ergosphere? Because metric doesn't depend on phi, so I consider delta 1 as ergosphere if I disregard phi. Disregard phi, simply consider into variable. So this restricted ergosphere is, there is a computation which I will skip, but the result is interesting, that this ergosphere is have equation of ergosphere r minus r plus equal to 0, r minus r minus equal to 0, where r plus minus is this expression. And miraculously, this coincide with event horizon for the Kerr metric. So this is the picture for Kerr metric. So because no dependence on time and phi, I writing only rho and zeta polar coordinate. So this, you see this ellipsoid look like, this is event horizon. This is upper event horizon, and this is inner event horizon. And there is also two ergosphere. This is upper ergosphere, and there is inner ergosphere. You see that this upper ergosphere, this event horizon inside, they have only two common points. They have two common points. So what I was mentioning here, that the event horizon is coincide with the restrictive ergosphere. So now definition. So event horizon is called stable if you take any family of metrics which for epsilon equals 0 coincide with the given matrix, and this family have psi epsilon family of event horizon which for epsilon equals 0 coincide with the given event horizon. So now one can consider perturbation in all stationary metrics, but it's enough to consider even in stationary metrics of this restricted type, this Kerr metric and metric of these examples, acoustic and electromagnetic, coincide here. So the theorem. So if you have restrictive ergosphere, and suppose ergosphere is also characteristic curve, so this means ergosphere coincide with event horizon, I will be calling such situation Schwarzschild type black holes. Yes, when you have event horizon and black hole or white hole coincide. So then this event, such event horizon is unstable. When event horizon coincide with the ergosphere is unstable as for Schwarzschild metric. And this is also for Kerr metric. Kerr metric is also unstable because if you consider this restricted event horizon, then it will be Schwarzschild type. So this is theorem of instability, but there is some remark to this. I will skip the proof. So the remark is the following. Suppose you have, say, Kerr metric or restricted ergosphere and event horizon. Then take any perturbation of this event horizon, any family of class curve that coincide with epsilon equals 0 to this delta 1. Then one can construct a metric. One can construct a metric such that this will be a black event horizon for this metric. Yes. So take this metric which is unstable, but if you take any perturbation of event horizon, you can construct metric such that it will be event horizon for such metric. Now, one more remark to this. You remember this example of acoustic where A and B. In this, event horizon was square root A squared plus B squared, and black hole or white hole was A. So when B is small, then black hole or white hole close to event horizon. And B, when B equals 0, you have characteristic direction. So in general, the black holes which we constructed before by using Poincaré-Benedict theorem, let us call them stable because they are really stable. And other are Schwarzschild type. So if the condition was that is characteristic, if this ergosphere is not characteristic but is close to characteristic, that this quadratic form is close to 0, then the constructed black hole will be close to ergosphere. So the picture is the following: that you have, for example, Kerr metric. It is unstable, but in any neighborhood you can find stable. You can find black holes close to Kerr black hole, which are of Schwarzschild type. And in any neighborhood of this, you can find also black holes, of stable black holes. So the quite complicated picture. There is a lot of black holes around, say, Kerr black hole. A lot of black holes are around the Kerr black hole. So if how much time I have?
5 minutes.
Oh, this is great. It will be enough. So I have one more topic, which is already not black holes, but it is again application of the theorem 1 of inverse problem, inverse 1. This is called, the topic called gravitational Aharonov-Bohm effect. The most difficult part is to know what it is. So what is definition of gravitational Aharonov-Bohm effect? So let us short review what electromagnetic Aharonov-Bohm effect. You consider Schrödinger equation outside, say, of obstacle. You assume that magnetic field is equal to 0. Magnetic field is curl equal to 0. So therefore, in any simply connected neighborhood outside of obstacle, your magnetic field can be eliminated. Yes, this is a gradient. Yes, so locally the situations that you have this electromagnetic field is equivalent to zero magnetic field. But this is only locally. Globally, it may be not true because domain is not simply connected. So this is a situation when you have locally is fine thing, and globally, you have gauge equivalent local, but you don't have global gauge equivalence. So now such situation, local versus global, appears in other topics. Yes. So here, for this case, so if we consider equation. We consider equation 1. This wave equation 1. Here, instead of gauge group, you have isometry group. You have, when you consider the equation, what I considered before, you have isometry group, yes? And you have these changes of variables, and metrics are isometric. I already showed this. These pages came from other papers, so there is repetition. And group of isomorphism, this is important sentence, that group of isomorphism play the same role as gauge group for magnetic field. So now, what is the question? Suppose we have you have local, that two metrics are suppose you have two metrics are locally isometric, but globally not isometric. The question is, what does it have physical impact? In fact, the rigorous definition what is Aharonov-Bohm effect is this, that if you have non-gauge equivalent magnetic field, then they have different impact. This is Aharonov-Bohm effect. And here, if you have, say, locally isometric is simply change of variable. We have no physical impact. But if you globally not isometric, to show that this will have physical impact. And what I will show that this is simply a reformulation of theorem 1. So if you consider the this equation, initial value problem, and the initial value problem, and you consider this is the theorem which already was here. This here. And you consider changes of variables. So the result is the following. The result is the following. If you have two metrics which are locally in neighborhood of some point isometric, but globally not isometric, they have different physical impact. Why? You consider if you two metrics locally isometric, you can make change of variable and extend it in the whole space to get a situation when you have two metric equal in the neighborhood of some gamma, equal in the neighborhood of the gamma. And then if they are not globally isometric, then the boundary measurement will not coincide for some f. Boundary measurement will not coincide with some f. Why? Because if they do coincide, then if Dirichlet-Neumann operator are equal, then the metrics are isometric, yes? Isometric. So this is the proof that non-globally isometric metrics have different physical impact. I make it very short so a concrete maybe better to start with concrete example. So suppose you have two metrics, which first of all, if you have two metrics, such expression, one can show that such expression is the same for all isometrics. Yes, if G prime is isometric, gamma prime is image of gamma, so such integral doesn't depend on isometry. Now, if you assume that metric is stationary and metric is called static if you have know these mixed terms, yes? G00 and this space-time, no zero time. So suppose we have that metric is stationary in only locally static, but globally non-static, Then this previous theorem shows that these two metrics make different physical impact. Their physical impact is different. So this is the proof of gravitational Aharonov-Bohm effect. So you deal with isometry instead of gauge equivalence. So this is all. Yeah.
Thank you. Questions?
Yeah.
When you define the black and white holes, you said that they're defined by saying that no disturbance can propagate. By disturbance, do you mean causal curves, or do you mean the support of the wave equation?
Support of wave equation. Yeah, support of wave equation. So that one can say that if equations have initial data have support in this part, they will stay support in this part. They will not go support. But this is equivalent to this description through light rays. Equivalent.
Other question, I mean, you had this non-stability of event horizons.
Yeah.
I mean, these counterexamples give the non-stability. What they mean physically, and do the examples, do they obey the positive energy condition?
Positive energy condition, I think I think is positive energy condition is related to Einstein equations, yes. And here I have pure wave equation ignoring everything else, yes. So there is no here condition. Simply, and this is stability in sense of the perturbation of metric, yes. When perturbation, even you start with Kerr metric, which is real, appears in satisfy Einstein equation, perturbation will be not. So perturbation under metric, that's it.
Other questions? I have a question. What do you think will be the variant, sort of three-dimensional version who uses Poincare-Bendixson theorem? So what do you need three to get?
Unfortunately, there is no three-dimensional.
What you would need?
What?
Or what you would need? Presumably, what sort of results three-dimensional you would need?
Result what I need. Result what I need is existence of closed characteristic surface. I need existence of closed characteristic surface. Then it will be boundary of black hole. Yes.
Maybe that means that you should not work in R3.
I am not working R3. Yes.
I mean, in X, you should be manifold. Some
manifold, yes. Manifold.
Then it will probably.
Manifold.
Some condition on geometry will allow.
It could be, but still, I think it could be. It should be geometry involved. Yes, it's not necessary. Should be complicated manifold, but geometry should be involved.
Okay. Other questions? Then thank you very much.